Hello, in this video we're going to talk about compact sets and the extreme value theorem. So just to remind you, the extreme value theorem over R was if you have a function from a closed interval to R, a closed and bounded interval that is continuous, then maximum and minimum exist. Now, we want to see what domains can we replace A, B in order to guarantee that a maximum and a minimum exists if the function is continuous. And the answer would be what we call compact sets. So first, what are compact sets, and some examples, and then a very important theorem. Okay, so here is the definition of a compact set. A subset A of Rn is called compact if every infinite subset of A has a limit point which lies inside A. So if I take a subset of A that is infinite, then it has a limit point, and not only that, but the limit point is inside A. So coming up with examples of compact sets is a little bit more difficult. So I'm going to do examples of things that are not compact, and then in the next theorem we will see how to find in fact compact sets. So we have two sets, R and 0, 1. We want to show these are not compact. So let's think about what is the negation of this statement. The negation is, if you want to show something is not compact, you will have to find an infinite subset of that set that either doesn't have a limit point, or it has a limit point but is not inside the set, or in fact all of its limit points are outside of the set. Okay, so if you look at R, you can find a sequence inside R that doesn't have a limit point. So the sequence would be 1, 2, 3, 4, etc. So this is an infinite subset of R without any limit points. Okay, so why is it that there is no limit point for this set? Well, it's not very difficult to see, because if you take a point, so it's 1, 2, 3, etc. If the point is not an integer, so if x is in R but is not an integer, then choose the smallest integer that is, or the largest integer that is less than x, and then the next one. So choose two integers that x lies in between them. Now choose a ball centered at x of radius r, where r is the distance between x and m, the minimum of the distance between x and m, and the distance between x and m plus 1. So the minimum of the distance between x and m, and the distance between x and m plus 1. If you do that, then this guy does not intersect with integers. So this intersection with z is empty, where you choose the radius to be that. Why? Because if your x is like right here, if you take a radius that is the smaller of these two, then the ball doesn't intersect any of the integers. And if your x is an integer, then the ball of radius 1 centered at x intersection with z is only x. So what does that mean? It means there is nothing inside the ball that is an integer except for the center, which means x is not a limit point. So in either case, x is not a limit point. Now, I talked about z, but of course when it doesn't intersect with z, it also doesn't intersect with positive integers. So that tells us that R in fact is not compact, because we were able to find a set that was inside R that was infinite, and it didn't have any limit points. Now we're going to look at the other set 0, 1. For this one, we can't really find a sequence that doesn't converge, it doesn't have a limit point. We can't find something like that because it's kind of trapped between 0 and 1. You can't go to infinity. But you can choose a set that, if you look at 1, 1/2, 1/3, 1/4, etc. This set is inside 0, 1, and its only limit point is 0. Its only limit point is 0. Okay, so we're going to show that there is no limit point that is inside 0, 1. Okay, that's all we need to show. We don't need to show its only point is 0 for our purpose. We only need to show that there is no limit point inside 0, 1. So if x is in 0, 1, then x would be, because x is positive and less than 1, then there is it lies between two of these consecutive 1 over n's. So that tells us x is between some 1 over n and 1 over n minus 1. And by the way, because I want to make sure that this sequence, this set is inside 0, 1, I'm going to start from 1/2. So it's either that or x is in fact equal to 1 over n. So either x is one of the 1 over n, or it is between two of them. In either case, there's a ball around it that doesn't intersect the set except for the center. So in the first case, in this case, take the ball of radius x in the first case, radius r centered at x, with r equals the minimum of the distance between x and 1 over n, and the distance between x and 1 over n plus 1. This is a positive number, and the ball centered at x of that radius doesn't intersect the set. So this intersection with S is empty if I call this set S. So I'm going to just call it S. Okay, that's if x is not 1 over n. If x is 1 over n, so in the second case, we'll just take the ball of radius r centered at 1 over n. This intersection with S is just 1 over n if you make sure that r is small enough. So you could take the distance between 1 over n and 1 over n plus 1, and 1 over n and 1 over n minus 1. So, I mean, it's actually, one of these is actually obviously smaller than the other one. This is a smaller one. But I don't want to just write down that argument because it's not needed. As long as you have a ball of radius, a positive radius that doesn't intersect the set or intersects it only at the center, then it is not a limit point. So that means x is not a limit point. So what does it mean? It means this set doesn't have a limit point inside 0, 1. Thus 0, 1 is not compact. Okay, so if we look at the example that we did, we did two examples. R is not compact because we could find a set that was infinite and it didn't have a limit point. 0, 1 was also not compact for a completely different reason. We could find an infinite set that, even though it did have a limit, but all of the limit points, in this case there's just one limit point, were outside of the set. Okay, so the first case was because the set R was unbounded. It informally speaking, it goes to infinity. The second one was because it was an open interval. It was not closed on both ends. So because of that, I need this definition. A subset A of Rn is said to be bounded if it lies inside some ball of positive radius. So anything that doesn't go to infinity, it means it just lies in some ball, is called bounded. So anything that lies inside a ball. Prove that a subset of Rn is bounded if and only if it is inside an open ball centered at the origin. In other words, if something is inside some ball, it would also be inside a ball centered at the origin. So, and that's not very difficult. So if you have something that is inside a ball centered at A, take the origin, and take the longest distance. So longest distance would be exactly on the other side. So this is the distance between A and 0. This is the radius. So just add these two and then draw a ball centered at 0. If you draw a ball centered at that, you'll get that the whole thing is inside this ball, which means we could just consider the ball centered at the origin. Okay, so I'm assuming that the set is bounded. So assume A inside Rn is bounded. By definition, there is a positive real number R and a point in Rn such that A is inside the ball of radius R centered at A because it is bounded. That's by definition of bounded. Now I'm going to show that in fact A is in the ball centered at 0 with radius S, where S is what we found is R plus the distance from A to the origin. So this one is R and this one is the distance from A to the origin. Okay, so we're going to show that. How do we show this? We're going to start with X inside A. So if X is inside A, that tells us that because A is a subset of ball of radius R centered at A, X is also inside ball of radius R centered at A, which means X minus A is less than R. Now I want to show that in fact the distance between X and its origin is less than S. So X is right here. I know this is less than R, this is less than R. This one is A, so this by triangular inequality would be less than R plus norm of A. It would be less than that. So we're going to have to invoke the triangular inequality. By the triangle inequality, the distance between X and 0 is less than or equal to the distance between X and A plus the distance between A and 0. Triangular inequality was exactly like this. If you call this one U, you call this one V, this one is U plus V. And now we know that X minus A is less than R because of that, and this one is just norm of A. But that was exactly S. So what does that mean? It means X is in the ball of radius S centered at the origin. So we just showed that if X is in A, X must be in ball centered at 0 with radius S. Therefore, A is a subset of ball of radius S centered at the origin, which is exactly what we wanted to show. We wanted to show if something is bounded, it is inside a ball centered at the origin. Okay, so the second direction is assume that A is inside a ball of some radius centered at the origin. We want to show it's bounded. But that just follows from the definition. So by definition, A is bounded, because it is inside a ball, open ball centered at the origin. Okay, so in other words, we can always assume that the center is the origin. It just sometimes simplifies our work. Now, we want to understand these compact sets. As I told you, in this theorem, we're going to in fact find all of the compact sets. This is a very important and interesting theorem. We won't be able to completely prove this theorem, but I will be able to at least convince you that this theorem is in fact true. So what is the theorem? This is called Bolzano-Weierstrass Theorem. A subset of Rn is compact if and only if it is bounded and closed. So we had two issues that where something was not compact. Either it was unbounded or it was not closed. This tells you that in fact those are the only conditions that we need. So let's look at the forward direction. a subset of Rn is compact if and only if it is bounded and closed. So suppose A inside Rn is compact. So what we want to do is we want to show it is in fact bounded. Okay, so we will show that it's bounded. So assume that it is not bounded. So assume A is not bounded. What does it mean? It means for any ball centered at the origin, A is not completely inside it. So that means, so by definition, A is not contained in any ball centered at the origin. And I'm talking about open balls, just to be clear. Although open and closed doesn't really matter here, because if it is open, if it is closed, you could just always put it inside an open ball. But just to be clear. Okay, so we know that it's not inside any ball centered at the origin, which means we can just basically create something that goes to infinity. How do we do that? So consider these balls. There is, if I take a look at the ball centered at the origin of radius 1, there is some element A1 inside this ball that is inside A. And if I take the center and I call, if I take the radius and make the radius K, there's also a ball of radius K centered at the origin, that this guy AK is inside that ball. So we can create this set. Now we created a set with norm of AK greater than K, because it's inside, it's greater than or equal to K, because it is not, oh, I meant not inside. It is not inside the ball of radius K centered at 0, which means its norm, its length to the, its distance to the origin is at least K. Now we will have to show that in fact this sequence does not converge. Okay, so first of all, since A is compact, by definition, the set A1, A2, A3, etc. must have a limit point. So it has a limit point, let's say B, inside A. Okay, so now we're going to show that in fact that's impossible. So I want to show that if I take this B, which is a fixed point, it's impossible to be a limit point of this set. Okay, so how do we do that? Well, if you look at these elements AN, they are getting, let's say the origin is right here, they are getting farther and farther and farther from this. So if you take these, every AN at some point would be outside of this. It's not going to be close to B. So if you take a ball, let's just take a ball of radius even just 1, centered at B. So if X is inside the ball of radius 1 centered at B, then the distance between X and B is less than 1, which means norm of X is less than or equal to norm of X minus B plus norm of B. But norm of X minus B is less than 1. So what does it mean? It means norm of X doesn't go to infinity. So it's less than 1 plus norm of B. Okay, so we showed that anything in here is going to have to be less than 1 plus norm of B. So what does that mean? It means if K is more than this norm, then AK is not inside this ball of radius 1 centered at B. So if you look at this ball of radius 1 centered at B, the intersection of that ball with A is finite. So B, because everything after K is outside of this set. This one, intersection with, I'm sorry, I meant this set. So if I call this set S, intersection with S is finite. But if it is finite, you could take the point inside S that is closest to B. So you have B here. You have a ball of radius 1 centered at B. You have only finitely many points. Let's say this point, and this point. Draw a ball that doesn't contain any of them, and that violates the fact that B is in fact a limit point. So draw an open ball centered at B with radius R, where R is the shortest distance from B to points in ball of radius 1 centered at B, intersection with S, excluding B. So this ball has no points in S except possibly B. Okay, so that completes the proof of the fact that if A is compact, then A would have to be bounded. Now we will have to show that if A is compact, A must be also closed. So we will show A is closed. Okay, so there are two ways of showing a set is closed. Either we show all of the limit points are in the set, or we show that the complement is open. So limit points seem to be a better approach here, because compactness also talks about limit points. So let X be a limit point of A. So we will have to show that X is also in A. So how do we show X is in A? So let's assume X is not in A. This is by contradiction. So assume that X is not in A, and we're going to get a contradiction. So what we're going to do is we're going to create a set, an infinite set, and we're going to show that X is the only limit point of that infinite set. So consider these. Consider balls of radius 1 over K centered at X. Now this ball intersection with A is not empty because X is a limit point. So that means you can find an element in here. So choose a K inside this ball of radius 1 over K centered at X that is also in A. Now this would be an infinite set because the points get closer and closer to X, and X is not in A. So this infinite set A1, A2, and so on. So the kth then would be AK. This is inside A. This is an infinite set. So there must be a limit point of this set S must be in A. But if you think about this, and this needs to be like worked out a little bit, but if you think about this one, if you look at X, X is really the only limit point of this set. This argument here would be very similar to the argument that we made that 0 is the only limit point of 1 over n. So that means if you continue with this, so there's a little bit of details that needs to be written, but that means X must be in A, which is a contradiction. Okay, so the converse tells us that if you have a set that is closed and bounded, then it would be compact. So what does that mean? It means if you take a subset of A that is infinite, it has a limit point inside A. Now, I'm going to give you the idea of the proof of this one. There's some parts of it that require completeness axiom in math, which we haven't gone over. But for the most part, the idea of the proof is just this. It just needs a little bit of details to be filled in. Okay, so we have a set. So suppose A is bounded and closed. So here is what we're going to do. Since it is bounded, it's inside some ball. Let me just look at an example in 2 dimension. It is inside a ball, therefore it's also inside a square. Let me, for simplicity, say the square that is inside is the unit square. So let's assume, and again, as I said, this has to be made completely rigorous. But let's assume, for the sake of argument, that the set is completely inside this square. So it is a set A inside this that is also closed. Now, I'm going to have to take a set S inside A that is infinite, which means it has infinitely many elements. Okay, so here's how we're going to find a limit point. We're going to take this square and we're going to divide it into 4 different equal pieces. So you have 4 squares here. Now we have infinitely many points inside set S. So since we divided into 4, one of these must have infinitely many points. Let's say this one has infinitely many points inside S. So now I'm going to write down what the limit point would have to be, and I'm going to write it down in binary. It's just a little bit simpler. So there are infinitely many points in here of S. So points of S could be here, could be here, could be here, could be here. One of these 4 would be infinitely many. Let's just say this one is infinitely many. Now, the limit point that I'm going to find would be the x coordinate. This is 1/2 and this is 1/2. The x coordinate would be in here and the y coordinate would be in here. So it would be 0 here and this would be 1. And this is in base 2. Base 2 representation of the limit point. Now we're going to take that and then we're going to divide this one into 4 pieces. Let's say we again know that one of these 4 pieces would have to have infinitely many points. Let's say this one has infinitely many points. So what does that mean? It means the x coordinate would have to be here and the y coordinate would have to be here. It means the second digit of x would have to be 1 and the second digit here would have to be 0. Then we're going to repeat the same thing. So let's just say you divide this one and then you figure out, okay, one of these 4 is infinite, has infinitely many points. Now again, it could be that all of them have infinitely many points. We just pick one of them, but definitely there is one. So let's say this one has infinitely many points. So that tells you that the third digit would have to be 1 for x and 1 for y. And then we keep doing that. As we see, this point is close to infinitely many points of this set because each of these squares have infinitely many points. We divide this one. Let's say this time we get this square. If we get this square, it means both of them are 0. We keep doing that, and this can be shown that this is in fact a limit point of the set, which means in fact the set A is compact. Now there are some details that why is it that this x and y are actually going to give us real numbers, because we are implicitly using base 2, and why these things are going to approach to a real number, and that requires completeness axiom. But that's really basically the proof. Okay, so that's very interesting. So now one of the main applications, and really the main reason we talk about these compact sets, is the extreme value theorem. Suppose A is a compact subset of Rn and f from A to R is continuous. Then f attains its maximum and minimum values. In other words, there exists x0 and y0 in A, for which f of x0 is less than or equal to f of x, less than or equal to f of y0. So if you take a function over a compact set, so for example, if you take a function from a closed square, which is a bounded and closed set, the domain is this, and the range, the codomain is R, there would be a maximum and there would be a minimum. So the proof of this one is a little bit more complicated, so I'm going to leave it at that. But basically the idea is to first show that in fact this image is not unbounded by the use of the fact that f is continuous and the fact that the domain is compact, and then show that in fact there is the largest value, a largest value, and a smallest value for that image. But I'm not going to go over the details of that. Okay, so that brings me to the end of this video. I will see you in the next video.